Hi everyone, this is module 3 feedback amplifier, output stage and power amplifier, lecture 2 feedback amplifiers. In the lecture 1 we learnt about different or general feedback amplifier, derivation for a voltage gain. Now in this lecture, so we are going to see the different topologies available for a feedback amplifiers, and we derive equation for input and output impedances. So there are basically four different feedback topologies as listed here. It is voltage amplifiers, current amplifiers, transconductance amplifiers, trans resistance amplifiers. So there are four different types of feedback amplifiers available. Okay, we call it as topologies, which is these are classified based on the sampling and mixing methods used in the feedback amplifier. Right, how output is sampled and how actually feedback signal is mixed with the input. That is how it is being classified. Based on that, you can also name these different amplifiers as series shunt feedback. That means, say, voltage amplifier is also called as a series shunt feedback amplifier because here the voltage is or a signal is mixed in series with the input. Whatever the feedback we are getting from this feedback network is mixed with Vs in series. Okay, you can see it is in series, right? So that is why it is series. And shunt because output, the second term always refers to the output and first term refers to the input. Okay, now second term shunt, we are taking the output signal or we are sampling the signal in parallel with the output, right? So that is why it is called series shunt feedback. Likewise, we have different names for these different amplifiers. Okay, shunt series feedback, series feedback, and shunt feedback. So based on the quantity to be amplified, whether you want to amplify voltage or current, and on the desired form of output, whether we are expecting an output voltage or a current, so these amplifiers are classified as voltage amplifier, where input and output both are voltages. For a given input we get an amplified output, so it is a voltage amplifier. So current amplifier for a current input and current output. Likewise, we have transconductance amplifier and trans resistance amplifier, where input will be a voltage and output is current. Okay, and input is current and output is voltage. So there are four types, basically four topologies we call: voltage amplifier, current amplifier, transconductance amplifier, trans resistance amplifier. So this is just a general example shown in this. Okay, this is the first one, voltage amplifier circuit diagram or block diagram, or what I can say. So we know for any given feedback amplifier there will be two blocks, major blocks. First one is an amplifier, okay, amplifier section, and another is a feedback section, which we learned in the previous lecture. So this is amplifier is having a gain of A and this is having a gain of beta. Okay, beta, gain of a feedback network is, we call it as a beta. Okay, so this is the feedback network, this is the feedback network. Without this it is an open loop amplifier. Okay, right, open loop amplifier. So we learned advantages of having a feedback. Okay, basically it is all negative feedback because amplifier always require or demands negative feedback. Okay, so these are the different representation of feedback amplifiers. So voltage amplifier, current amplifier, transconductance and trans resistance amplifier. So all looks kind similar. The difference is in the type of input voltage, input signal we apply, or the type of output signal we sample, right? So in this voltage amplifier we can see that input is voltage and sampling what we are doing is also an voltage, so it is an voltage amplifier. It is also called as series shunt feedback amplifier. Series shunt feedback amplifier. Right? So you can see current amplifier, both input and output parameters are current, Is and I0, and it is called shunt series. You can see shunt because the feedback signal is mixed with an input signal in parallel. So it is a current source. Please remember, there should be a parallel in connection. Right? That is how you can mix the current with the current. Right? So this is shunt connection and this is series connection. Right? So shunt series feedback amplifier, and the input signal is a current source. Output is also a current. Right? So we are getting a sample out of this. A part of the output signal, that is current, is fed back to the input, and the output of this feedback network is again fed back to the input. Right? So the same way as voltage here, we are taking voltage here and we are feeding a voltage here. Okay. A transconductance amplifier, here also it is a voltage input and output is a current. In trans resistance it is opposite, input is current and output is voltage. Right? So this is the you can do some comparison over here, block diagram comparison, and what observations you can make from this. You can see voltage amplifier and trans resistance amplifier output circuit is same. Output circuit is same. Right? And if you see current and current amplifier, transconductance amplifier output is same. Right? You can see it is output is same. Output circuit remains the same. So why I am telling you this? Further, when we derive equations for input and output resistances of these, then whatever you apply for the, say for example, if you want to find the input resistance or impedance of an voltage amplifier, right, which looks similar to the transconductance amplifier, the input circuit, you can see it is similar here. But output of this is not similar to this, it is similar to this, right? Anyway, wherever you find the input output circuit same among these four, then you can use the same equation. The input resistance or output resistance is represented by the same equation, right? So anyway, we will see all those stuff in the coming slides. Voltage amplifier. Let's take one by one. Voltage amplifier, and it is also called as series shunt feedback. So these are all the example circuit of voltage amplifier. So this is the well-known voltage amplifier. What type of amplifier it is? It is an op-amp amplifier basically, and it is a non-inverting op-amp amplifier. It is a non-inverting amplifier, right? Because input is connected to a non-inverting terminal. Okay, so that is why it is a non-inverting amplifier. A non-inverting amplifier is basically an voltage amplifier. Okay, and you can see this is a feedback network. This is the feedback network. Okay, and it is a voltage divider network. Okay, you have R1, R2. You can replace this by RF also, but really doesn't matter. And this feedback network, as I said, it is a voltage divider network. You have to remember this, right? Now, so we say it is the given voltage amplifier, for a given voltage amplifier, we say feedback is negative only when the feedback signal and applied original signal are in same direction, right? Means if Vs is increasing, Vf should increase. If Vs is decreasing, Vf also should decrease. So then only we say it is a negative feedback, right? So in order to justify that, you can just analyze this circuit. So whenever I increase the signal input, okay, Vs from its normal value, if I increase, then definitely output is also increase, right, for a given gain of the amplifier, okay, feedback amplifier. Okay, for a given input voltage, if I increase the voltage, then output also increases. That is what I have written here. Vs is increase if increases, V0 also increases. If V0 also increases, Vf also increases. Please remember, Vf also increases. So Vi here is equal to Vs minus Vf. Vi is equal to Vs minus Vf. Right? So why Vf increases here? Why Vf increases? Because V0 increases. So why V0 increases? Because Vs increases. So with this V0 is a voltage comes under voltage divider network. We need to apply voltage divider rule. So wherein I can say Vf voltage at this point is equal to V0 applied voltage into voltage across you want to measure, the resistance across which voltage need to be measured, that is R1 divided by total resistance R1 plus R2. So Vf is directly proportional to V0. So any increase in Vs, increase in V0, increase in Vs. So increase in Vs leads to increase in Vf. That tells you it is a negative feedback. Right? So and we are both considering a voltage here, so it is a voltage amplifier. Right? So we have another example. You can see we have another example here. Okay, where we have two cascaded amplifiers in this case, right? And it is a MOSFET. We have a MOSFET, two MOSFETs, Q1 and Q2, and it is a common source configuration. These two amplifiers are in common source configuration because source is connected to ground and it is common between the input and output, and this is common between input and output. Right? This is a two-stage amplifier. And the voltage Vi between gate and source, voltage Vi between gate and source is nothing but VGS. This is the gate terminal and this is a source terminal. So it is a VGS, right? And this VGS is nothing but Vs minus Vf, the applied voltage and the feedback voltage. Vi is equal to Vs minus Vf, that is Vi, and it is small in quantity compared to this, no doubt about it. So let's analyze this, right? So whenever as I said in this case, here also if you increase Vs, Vf should increase, so that you can call it as a negative feedback, right? Whenever Vs increases, right, it is a MOSFET, you are applying more voltage to the gate terminal, definitely drain voltage also increases. V01, I am calling it as V01. Okay, so V01 also increases. And please remember, this V01 is connected to the gate of the next transistor. So voltage at this transistor start increasing at the gate terminal. Right? Because of that, output of this transistor also increases here. V0. This is V0. Right? V0 start increases. If V0 start increases, definitely Vf increases, because we know, we learned this from the voltage divider rule. Right? Here also voltage divider rule apply. Right? Vf is directly proportional to V0. So Vf start increasing. So Vi is equal to Vs minus Vf. If you start increasing Vs, Vf start increasing. Right? Okay. So if you take another example, right, this one. Right? So we are not really getting into the deep analysis of these examples, right? So here we are trying to give an idea how the negative feedback is achieved with these examples. And you can see this is common gate configuration because gate is connected to ground, okay, and input is applied to source here and drain is taken as an output, right? So here in this case, whenever Vs increases, right, input voltage increases, output also increases, right? Output also start increasing, right? So when output increases, again voltage divider rule, Vf start increasing, right? So this is a common gate configuration. This is common source configuration. It is a cascaded amplifier and it is a simple non-inverting amplifier, right? So these are all having different patterns, right? This is a cascade amplifier, this is a single stage, this is a single stage amplifier, right? So based on the need and application, different circuits are used, different voltage amplifiers are used. All these are voltage amplifiers. So we can have BJT amplifiers also. These are FET amplifiers, right? And this is op-amp amplifier. We can have a BJT amplifier also, right? So let's take the next one, current amplifier, right? So this is the circuit, right? Current amplifier, both input and output are current. Input source is current source IS, right? So parallel internal resistance of which is RS, okay, and output is I naught, okay, load RL, it is common, and we have a basic current amplifier and feedback network, right? This is same as the circuit we saw earlier, right? This one, right? Same. You can see this is shunt series feedback. It is also called as shunt series because input is feedback signal is mixed with the input in shunt, right? So that is why shunt. Series means output is taken in series, right? Sampling of output is done in series, right? That is why it is shunt series feedback. We learned that earlier. So this is one configuration. This is also a two-stage amplifier, right? Right, common source, right? This common source, right? Here you can see IS is equal to II plus IF, or else you can say II, the current which is flowing into this source of Q1, is equal to IS minus IF. In either way you can consider, right? Any increase in this current, source current IS, definitely there is increase in this. Definitely there is a increase in this voltage, and this voltage I am calling it as V01. I am calling it as V01. Increase in IS, definitely it will increase II. If there is increase in II, definitely there is an increase in the output of this first stage, that is V01. If this increases, the same is applied to the gate of the next transistor, that is Q2, and please remember it is P channel. Okay, you can see the arrow mark here. We have an arrow mark, right, which is showing inside. Okay, here you can see the arrow mark is showing outside. If arrow mark is outside, this is the N channel FET, and if it is inside, arrow mark is inside, then it is P channel FET. For a P channel, if input voltage is increases, output current decreases. Output voltage decreases, hence the current decreases, right? If current decreases, voltage which develop across this also decreases, that is RM, which is connected in series with RL. Okay, the current IF is flowing through RF, please remember, and whenever there is a decrease in I naught, there is a decrease in voltage across this RM. Voltage across this RM also decreases. If voltage across this RM decreases, means more current starts flowing through RF, okay, through RF and to RM. Please remember, because resistance decreases, so that voltage across this also decreases. Not physical resistance, I can say. Current will decrease, right? So in order to compensate for that, IF will start increasing, right? So IF increases. So ultimately, IS increases, IF also increases. So it tells it is a negative feedback, right? So this is about current amplifier. So let's move to the next one, transconductance amplifier. Again the diagram, same diagram is you can see here. Transconductance amplifier, input is voltage and output is current, right? Input is voltage source and output is current, and it is series feedback because both voltage sampling at the output and current signal mixing at the input are in series, right? You can see it is in series. That is why it is series feedback, right? Take this example. This is one amplifier circuit, transconductance amplifier. Please, this is a transconductance amplifier where we have an input as a voltage source. So you can see we have a voltage source. So we have a voltage source here, and it is applied to the inverting terminal of an op amp. This is a differential amplifier, no doubt, and the output of which is opposite to the input, right? Because it is an inverting amplifier. Please remember, it is an inverting amplifier. If you apply positive signal, you get negative signal at the output. If you apply positive signal, you get opposite to this input, right? That is taken as an output, right? So whenever Vs increases. V01 start to decreases. Means if you are positive, it will give you negative. That is what the meaning of it, right? Or else if you increase the voltage, or this V01 will increase in negative direction. That is what the meaning. Okay. V01 will decrease. Please remember as a P channel FET. So current I0 will increase. It will not decrease, it will increase because input is decreasing here. Means it is going more negative. Right? For a P channel, negative gate gives you more output current. Right? So I0 increases. When I0 increases, Vf also increases. Current flowing through this Rf increases. So V is equal to I into R. So Vf also increases. So Vf is connected to the positive terminal of the op amp, or non-inverting terminal of the op amp. So Vf also increases. So increase in Vs, increase in Vf. So it is a negative feedback. This is a negative feedback. Right? So we have one more example here. Right? One is a common source, and this is common drain configuration. So same thing applies to this also. This is transconductance. One example of a transconductance amplifier. Transresistance amplifier. Right? You can see three different examples we have in this diagram, in this slide, sorry. And this is the diagram where we have an input current source Is and output voltage, okay, V0. And it is called shunt feedback because sampling, output sampling and input signal mixing is done in parallel. So that is why it is shunt feedback. Right? Now this is op amp amplifier. Okay. So input is applied to the inverting terminal and RF feedback network is connected between the output and the input. Please remember. And Is is equal to IF minus II. IF plus II, where II is equal to Is minus IF. If any increase in Is, II, which is current which is flowing into the op amp, also increases. Right? And also which makes later IF to increase. Right? So Is increases, IF also increases. Right? The same scenario or same explanation is also holds good for this. Right? Just try to analyze this. This is the BJT amplifier. Please remember, it is a BJT amplifier, right? So these are the examples of transresistance amplifier. Nothing much in this. Okay. Okay. Let's get into the derivation. Feedback voltage amplifier. So this is the equivalent diagram for an voltage amplifier. Actually, this section is an voltage amplifier and this section is a feedback network. That is what we saw earlier, right? In these diagrams, these are the blocks, right? So if I take individually all these four topologies and I can write an equivalent circuit of both amplifier section as well as feedback network like this, right? So this is the input side section and this is the output section of an amplifier. Same for the feedback network, and we know how to write this, right? This is an equivalent model, right? So Vi into Ri, right? This is A into Vi, okay? Constant dependent source, right? And this is internal resistance R0, and this is the internal resistance of an amplifier, open loop amplifier Ri, and this is the internal output resistance of an amplifier R0, okay? And this is Vi, which actually applied across the terminals of the input terminals of the amplifier, that is Vi, right? Okay, this is an equivalent circuit, right? And same as this one, beta into V0, right? The voltage Vf is equal to beta into V0. Why it is beta into V0? Because the input to this feedback network is V0. This is the sampling we have taken from the output and it is given as an input for this, right? So V0 is an input for this circuit, okay, this beta circuit, and gain of this beta circuit is beta. So output of this circuit is Vf. So Vf is equal to beta into V0. or beta is equal to V naught by Vf. Gain is equal to output by input. Vf by V naught equal to beta, or else Vf equal to beta into V naught. Okay. Now, apart from this, you can see we have a source, actual source, Vs, okay, voltage source we have, right, and we have a current II which is flowing into this amplifier, right, current II which is flowing into this amplifier, and this is a feedback signal mixing with this, right, that is Vf. Of course, this is minus Vf in this particular case, right, minus Vf. Right, you should see the term, polarities of this. Now, for this, if you want to find input resistance and output resistance, this is how it should be, right? Looking into the input side from the source, looking into the input side, it is RIF. It is a input resistance or impedance with feedback. Input resistance with feedback. This RI is an resistance without feedback. This is resistance with feedback looking into the input side, and like the same way, this is output resistance or impedance with feedback, or not F, looking at the output, right? So for this particular case, voltage amplifier, let's find the voltage gain. So we already derived in the last lecture voltage gain expression, right, general voltage gain expression for an feedback amplifier. The same is also applies for all 4 different topologies. One is shown in this as an example, right? For the voltage amplifier, we have shown the voltage gain. For the rest of the feedback topologies, you can carry out that as an exercise. Now, voltage gain. So V naught here, V naught output voltage is nothing but A into Vi. Whatever the voltage you are measuring here between these two terminal means between this point, right? It is nothing but A into Vi. A into Vi. For a given input voltage, gain is A. Gain of this amplifier is A. Okay. A into Vi is nothing but V naught, or V naught is equal to A is equal to V naught by Vi. That is the gain expression. We know that. So which is equal to, I'm going to retain A as it is. What is Vi in this case, considering feedback? So Vi is nothing but Vs minus Vf. Vs minus Vf. Now substitute, we get this. What is Vf? What is Vf? Vf is nothing but beta times V naught. Vf is nothing but beta times V naught. Beta times V naught, Vf. Correct? So please substitute this Vf in this equation so that you get this. Is it clear? So A Vs minus Vf is nothing but beta times V naught is equal to V naught. So V naught in LHS and RHS we have V naught. You please solve for V naught, means take a common V naught, right, and you get A Vs is equal to 1 plus A beta or beta A into V naught. So V naught by Vs, V naught by Vs is the actually gain with feedback, right, which is equal to A divided by 1 plus beta A. Take this to LHS, take this Vs to RHS, you get V naught by Vs, that is nothing but a feedback gain, gain with feedback, right? We are familiar with this equation earlier also, right? A by 1 plus A beta. Gain of an feedback amplifier is decreased by a factor of 1 plus A beta or beta A compared to the open loop gain of an amplifier, that is A. A is a gain of an amplifier without feedback. If you have a feedback connection together, okay, all these together, it is A by 1 plus A beta, right? So gain is reduced by a factor of 1 plus. This is the only disadvantage you can say of having a feedback, not only in voltage amplifier, in any of the amplifier, right? But it has many advantages, right? So why V naught by Vs? Because this is the extreme end V naught, and the actual input we are applying is Vs. So V naught output voltage by input voltage, right? So this is what I am expecting out of this, right? So ultimately we get this expression. So similarly, for a different feedback topologies, one can derive equation for voltage gain, but ultimately for any feedback topology we get the same expression, right, irrespective of the topology. You can check it out, right? Anyway, we will see that later. So how to find the input resistance of the voltage amplifier? Okay, so input resistance means we are finding input resistance with feedback. Without feedback it is simply Ri. Input resistance, output resistance is simply R naught, but we are finding with feedback, right? So RIF, R is basically R is equal to V by I. So in this case V is Vs, I means II, the current which is flowing into the op-amp, amplifier, right? So applied voltage Vs, current flowing through this is II. Okay, so we are looking from this side, RIF is equal to Vs divided by II, voltage by current, R is equal to V by I. So here what is II then? What is II? By looking into this diagram, you can see current flowing through this resistor Ri is equal to Vi by Ri, Ohm's law, Vi by Ri. What is Vi? It's the difference of these two. Difference of Vs and Vf gives Vi. Right? And if you solve for it, you get Vi is equal to Vs divided by 1 plus A beta. Right? So here also you can see how this actually comes. Now I can explain this. See, here gain is reduced by the factor of 1 plus beta I. That ultimately tells your input voltage also reduced by a factor of 1 plus A beta compared to the original input. Right? Then only it is possible. If this is possible, then only this is possible. Right? Okay. So Vi is equal to Vs by 1 plus A beta. You need to divide this input voltage by an amount 1 plus A beta or beta I, one and the same, right? That is Vi. Okay, once you get this, please put this Vi in this equation so that you get this Vs divided by 1 plus A beta into Ri, and you please put this equation II in the input resistance equation. So RIF is equal to Vs, I'm going to keep it as it is. II is nothing but this Vs divided by 1 plus A beta into Ri. So Vs will get cancelled and you will left with 1 plus A beta into Ri. So this is the expression for input resistance for an voltage amplifier. You can see input resistance of an voltage amplifier with feedback is increased by a factor of 1 plus A beta compared to the input resistance of an open loop amplifier without feedback. Means without feedback the resistance is Ri. Okay, it is multiplied by 1 plus A beta, means it is increased by 1 plus A beta. Okay, that tells you the input impedance of an voltage amplifier is high and output impedance of an voltage amplifier is low. We will see this, right? We will derive equation for this, right? For timing, you see the input resistance of an voltage amplifier is high, right? That is one of the advantage of having a feedback, right? You can choose a particular topology so that it suits your application, right? If you want high input impedance and low output impedance, one can select voltage amplifier, right, which provides you a high input impedance and low output impedance. That is what we are proving now, right? And this diagram is an equivalent circuit of this entire voltage amplifier, right? All together it is RIF, it is AF into Vs, applied voltage Vs, AF into Vs. Instead of A into Vi, it is AF into Vs. This is RIF all together. Right? This is R naught F. We will see R naught F next. Okay. Now let's see the output impedance. Before we start finding the output impedance of this voltage amplifier, so you need to do some changes to this network, right? So here you need to make this equal to 0. Vs is made equal to 0, and one needs to apply a voltage source at the output terminal in order to find the output impedance of the network, and this procedure is common for all different types of amplifiers in order to find the output resistance or impedance of the amplifier. So that is why in this part of the network, so I am making it as Vs input signal as 0, that is short circuited. S dash is short circuited. S dash is short circuited, right? And Vx, the voltage source, new voltage source is brought into picture here, right? So Vx, and rest of the things remain same, no change. Now output resistance R0 F is equal to Vx by Ix. Vx by Ix is R0 F. Now we need to measure the output impedance. I am not interested in the input side, I am interested in the output side. Correct? So R is equal to V by I. What is V? Applied voltage Vx. What is current? Ix. Right? So here, what is Ix now? Right? Ix, which is flowing through the resistance R0, internal resistance R0, right? Resistance R0 is equal to Vx minus A into Vi. These are the sources, right? Connected to the extreme ends of the R0. So current flowing through this is difference of voltage divided by the resistance. Correct? Potential difference. So Vx minus A into Vi divided by R0 gives you Ix. Then what is Vi? What is Vi? Vi is basically Vs minus Vf, but Vs equal to 0, so Vi is simply minus Vf. So Vi is simply minus Vf. Right? What is Vf? What is Vf? What is Vf? Vf is nothing but beta times V0. Beta times V0. So V0, now we consider it as Vx. Right? We don't know, there is no V0 now. We have a source at the output, so it is Vx. So Vx. So Vf is equal to beta times Vx. Vi is equal to minus Vf. So please put this Vf in this expression. So it becomes minus beta times Vx. Vi is equal to minus beta times Vx, and that expression is placed in this Ix. So that is what, this is what you get. Vx minus A into Vi is nothing but minus Vf. Minus Vf or Vf is nothing but beta times Vx. So it is minus beta times Vx divided by R0 as it is. Minus into minus plus Vx A into beta Vx divided by R0. Right? This is Ix. You can take Vx common in this case so that you get 1 plus A beta. Okay. Now Ix we got. Please put this equation in the R0 equation. So it is Vx divided by Ix. Ix is nothing but this. This is what it is. Is that right? Vx is taken as common factor. 1 plus A beta divided by R0. So Vx will get cancelled. It is R0 divided by 1 plus A beta. So resistance, output resistance with feedback for an voltage amplifier is equal to R0 divided by 1 plus A beta. Now in this case what this tells is output resistance is decreased by a factor of 1 plus A beta if you have a feedback. For an voltage amplifier, output resistance with feedback is reduced by a factor of 1 plus A beta to the original output impedance of the amplifier alone, okay, without feedback. Our output resistance without feedback, R0 is output resistance without feedback. With feedback is reduced by a factor of 1 plus A beta, and this is a common factor in most of the expression. Right? In the input section it is increased by the factor, and the output section it is decreased by the same factor, and also the gain is reduced by the same factor. Please remember, right? So that is how you should remember the expressions, right? So what I can conclude with this voltage amplifier, if our application demands amplifier to have a high input impedance and low output impedance, one should go for voltage amplifier. Okay. Now let's take another amplifier, transconductance amplifier. Okay, transconductance amplifier, where input is a voltage, output is a current. We know that, right? You can see the equivalent diagram of that. Okay, this is the equivalent circuit of this, right? And here input resistance with feedback is directly given 1 plus A beta into Ri. The reason is the input circuit of this as well as the voltage amplifier, another topology, it remains same. This is series connection and it is a voltage source. It is a series connection and it is a voltage source. So I have not derived it. Okay, if you at all if you have any interest, you can do it one more time, right? But it remains the same for both for voltage amplifier and transconductance amplifier. Now I am interested in the output circuit because output is different. Now we now have a current source rather than voltage source here in the equivalent circuit, and it is a dependent source, right? So it is VI RI, A into VI or not. It is not in series, it is in parallel because it is a current source, right? And it is I naught, right? Fine. Okay. Right, you can see Vf is nothing but beta times I naught. It is not beta times V naught now. It is beta times I naught because I am sampling current here, not the voltage. I am sampling the current, not the voltage. Right? So that is why input is current for this feedback network and output is an voltage. So beta is equal to Vf by I naught, or Vf is equal to beta into I naught. Beta into I naught. Okay. So in order to measure the output impedance, as I said earlier, you need to have a source at the output and you should short circuit the input. Source at the output, this time it is a current source because I am interested in current at the output now, because it is a transconductance amplifier, right? Now R at F is same, Vx by Ix, right? What is Vx? Basically, I will come to this later. What is Vx? Vx, this is Vx. V is equal to I into R, right? V is equal to I into R. Vx is equal to I into R. So I, you have two sources and both are flowing in opposite direction, no doubt, right? So it is Ix minus A into Vi into R naught. So V is equal to I into R. Simple Ohm's law. Everything is Ohm's law in this case, right? So further, what is Vi? Vi is nothing but minus Vf because it is short circuited here. Input is short circuited. Vi is nothing but minus Vf. We learned it in the last slide. So Vf is equal to what then? Vf is nothing but beta times I naught. Beta times I naught. In this case, I am not interested in I naught. I am calling output as a source current, replaced output current by a source current Ix. So I naught is replaced by Ix here, right? So minus beta times Ix. Vi is equal to minus beta times Ix, right? So the same is substituted here. In place of Vi, I am going to substitute this minus I beta times Ix. Minus minus is plus, right, into R naught. Right. Take Ix as a common factor. It is Ix into 1 plus A beta into R naught. So that is what Vx is. Put this expression in this R naught F expression. Okay. So Vx is equal to Ix into 1 plus A beta into R naught. So where Ix get cancelled, right? Ix gets cancelled. So left with only 1 plus A beta into R naught. Now, for a transconductance amplifier, output resistance with feedback is increased by a factor of 1 plus A beta. right? It is 1 plus A beta into R naught. It is increased. Output resistance increases for a transconductance amplifier. So, if application demands an amplifier such that its input impedance and output impedance, or input resistance and output resistance, must be high, then one should go for transconductance amplifier, right? So this is transconductance amplifier. This is the RIF and RNF. And also you can find what is gain of this transconductance amplifier. Okay, the similar way we did it earlier, right? Voltage gain, we found it for a voltage amplifier, okay, through these expressions. Similarly, you can do it for this transconductance amplifier also. Right? Same results, right? You take it as an exercise and do it. Okay. Now, let's go for the next one. Trans resistance amplifier. Trans resistance amplifier. Okay. Here output resistance is not derived because output circuit here is same as the output circuit of the first. Okay. Right. So it is R naught by 1 plus A beta. Right. And input circuit, here we have a current source IS. Right. In this case it is a voltage, and this case it is a voltage. Now it is a current source. It is quite different. So that is why we are again solving for input resistance for a trans resistance amplifier. Right. So what is RIF in this case? RIF. Please remember, IF here is equal to beta times V naught. IF is equal to, right, feedback current, right, is our feedback signal is equal to beta times V naught. Right. Here the dependent source is A into II, right, because it is a current source, you need to take II here instead of VI, right. So anyway, RAF is nothing but VI divided by IS. It is VI divided by IS. R is equal to V by I, where II, or current which is flowing through this resistance Ri, is IS minus IF, where IF is beta times V naught, where V naught is the thing but A into II, same thing. So ultimately IF you can replace with this, right? That is why the expression II is equal to IS minus of, instead of IF you can see this. You can solve for II here, because in LHS, RHS you have II, right? You get this expression, put this expression here, right? So that you get RAF is equal to Ri divided by 1 plus A beta. In this trans resistance amplifier also, input resistance is reduced by a factor of 1 plus A beta. In the previous two cases it is increased by the same factor. Here also it is increased, that is what we have considered. But here in trans resistance it is decreased by a factor of 1 plus A beta, and output resistance also decreased by a factor of 1 plus A beta. Okay, output circuit of this and the previous same, so I am not doing it again. Okay, right? You can try for different input and output resistance for different topologies in the same manner, right? So if any application demands both input and output impedances should be low for a given circuit, then one can go for trans resistance amplifier. This is current amplifier, right? So it leads to the same expression. Once you solve for this, it leads to same expression. Okay, with the same steps you need to follow, right? You can do it. Same doesn't mean that you can use the same expressions whatever we learned earlier. Okay, it is not like that. You need to apply the, you should do analysis of it, and you should derive these equations, right? You do it for all the topologies independently so that you get these expressions, right? Method remains the same, right? Now, just look at the comparison of feedback amplifiers, right? So have a glance of these different equivalent circuits of feedback amplifiers, right? Series, shunt, series, shunt, series, right? Okay, here we are using a voltage source, voltage amplifier, current amplifier, current source, transconductance, voltage to current, trans resistance, current to voltage, right? So these things you should remember, so which will help you to write correctly in the examination. So this is a consolidated parameters of an feedback amplifiers, different topologies, right? So these are the different amplifiers or topologies we have, and these are the different parameters of the same, right? Gain, input resistance, output resistance, and you can see gain remains the same. Okay, you can derive this expression. Okay, it remains same irrespective of the topology or amplifier you have, right? The only difference is what input and output means in these different amplifiers, right? Here it is voltage, it is current, voltage, current, and current. And so this is where it differs. This is where the resistances of the circuit differs, right? See, green, these green colored, these are increasing resistances, right? And other one, it is decreasing resistances with feedback, right? As I said, voltage amplifier increase in input resistance, decrease in output resistance. Similarly, transconductance, both input and output will increase. In trans resistance, both input and output will decrease, right? And in current amplifier, input is decreases, resistance decreases, and output resistance increases. So these are just this just shows the comparisons of input output resistances of different feedback amplifiers. So what you can do with all this knowledge is you can derive expression for gain, for transconductance amplifier, trans resistance amplifier, current amplifier. I did it for voltage amplifier. You use the same method to derive expression for gain for all these three different, and also you can do solve for input and output resistances of the different feedback amplifier. I have not shown for all, right? So you can do it, you can check it out, right? Thank you.